Hi, hello everybody. In last couple of classes, what you have been seeing is propositional logic. We have defined what a proposition is. Proposition is nothing but a declarative, unambiguous statement which is having its truth value either as true or false, but not both at a given point of time. And then we have studied some of the connectives like and, or, not, exclusive or, implication and biconditional implication. Then we have constructed compound statements, compound predicates, and then in the last class we have seen when do you say two compound propositions are semantically equal though they are syntactically different. Though propositional logic is very much applicable in most of the disciplines, it does have some limitations. It cannot adequately express the meaning of some of the statements in mathematics and natural language. It cannot infer some things nicely. For example, suppose we have got a proposition called every computer connected to bits network is functioning properly. This is the proposition that I am talking. This is definitely a proposition. We should not have any problems with this. And because I am saying this is a truth statement, hence this is a true statement, and this is very much a proposition. Then let us look at another proposition called say COMP121 is another computer which is there in bits network very much, and say I am saying its truth value of this particular proposition, that is COMP121 is functioning properly. This another proposition and its truth value is true. Now we have got two propositions. Earlier one, every computer connected to bits network is functioning properly. Another proposition like COMP121 is functioning properly. Without this propositional logic in place, it is commonsensical to think that the second proposition can be easily inferred from the first proposition. But unfortunately, propositional logic does not give us any ground to prove that Q can be deduced from P or Q can be inferred from P. This is one of the limitations, and these limitations have been addressed by a with the generalization of propositional logic called predicate logic. Basically, predicate logic is an extension of propositional logic that permits concisely reasoning about whole class of entities. What I mean class of entities we will see in some time. If I got a class of entities at a given point of time, I will be able to say this class of entities is true or not. If I know a given class of entities is true, I will be able to deduce a lot of things about each individual entity there. This it enables us to do it, with which we can do wonders. This is what is predicate logic about. It is basically a generalization of propositional logic. Basically, this predicate logic rely upon one thing, that is, it distinguishes a subject from the predicate of a given sentence. What vocabulary I am using is not foreign to us, because the same vocabulary that we learned in English grammar, the same thing I am using it now. We will go back to our English grammar. When I say Krishna is sleeping, what is the subject here? Subject is Krishna, and what is the predicate here? Is sleeping is the predicate. Okay, so here this has been fully exploited by this branch called this particular branch called predicate logic. Basically, if you take this example, Krishna is sleeping, how we represent in predicate logic is something like, I will say X is sleeping, I'll say Px is equal to x is sleeping, I say Px is a predicate. When I substitute x with a given object like Krishna, it becomes a meaningful preposition. In place of x, if I substitute Krishna, Krishna is sleeping. If he is sleeping, if the truth value of the statement is true, otherwise it is false. I can substitute Rama, and if he is sleeping, the truth value is true, otherwise it is false. So this Px is what is called as predicate, and when I substitute in place of x any real time any object, I will get a preposition out of it. Or otherwise you can see it like this. Basically, a predicate is a function between two things, between the actual objects and the set of prepositions. In this example, when I say x is sleeping, what are the objects? I can consider all human beings as the objects. This is set of all human beings on one hand, and on the other hand, I'll get all the prepositions. Give a subject, I'll get a preposition. Rahim is an object, I'll get a preposition, that is Rahim is sleeping. So basically, predicate is nothing but a function that is acting on the set of all subjects or objects to the prepositions. And let us, before we go into actual working of predicate logic, we will see the applications of predicate logic. With the predicate logic, we can formally write unambiguous mathematical statements which are very concise, clear and perfect. We can write axioms, we can write theorems, and we can prove the theorems. This is very much useful in proving mathematical, in coming up with mathematical theorems and proving as well. And if you have got any mathematical system, with the predicate logic we will be able to define what a mathematical system is, and with the axioms that we have put in the system, we will be able to prove some of the theorems that we can derive from. And if you have to see practical applications, they are enormous. If you have got to develop a complex system, then most of the times people prefer to write the requirement specifications in predicate logic. And in the great subject called artificial intelligence, the knowledge has been represented by making use of predicate logic, and in databases it is used at a number of places like query engines and all those things. So applications are really enormous. Unless otherwise we have got a better grip on this subject, we will not be able to work on these great subjects. Let us see conventions. When I say x is sleeping is a predicate, what I said is when I say Px is when I define Px as x is sleeping, I said P is called a preposition, is called a predicate. Generally, we define variables. Here, what is a variable? X is the variable. All these variables are denoted by small letters. Most of the times it is by x, y, z. And actual preposition functions, actual predicates by capital letters called P, Q, R. Okay. And here one small thing we better understand. Suppose we have got a preposition, another predicate called Px. Px that is defined as x is a prime number. This is a predicate that I am saying. Can I say Px a preposition? No, never. But when I can say what is the prepositions inbuilt behind that, when I substitute a value in place of x, that becomes a preposition. When I say, in this case, when I say p of 3, this is a preposition because I am substituting x with the value, with the natural number 3. Then p3 becomes 3 is a prime number. It may be true or it may be false, doesn't matter. p3 is a preposition, but not p is a preposition. P is called a predicate. We never call p as a preposition. When we substitute a value with the variable, it becomes a preposition. Let us look at another little complex predicate called pxyz. Say pxyz is defined as x gave y the grade z. This is a predicate. And if I substitute, say, Mike in place of x and Mary in place of y and A in place of z, then I get a nice preposition called Mike gave Mary the grade A. This becomes a preposition, but the earlier one is a predicate. Okay? Suppose I am talking this particular predicate with respect to BITS University. Then x, from where the values of x will come? Obviously, professors of BITS University. From these, x assumes the values from, x takes the values from, y assumes the values from the set of all students who got registered to BITS University, and z gets values from a small set called A, B, C, D, which are nothing but grades that you will be given. These sets from which x takes values from is called universe of disclosure. In this case, what is the universe of disclosure for x is the set of all professors from BITS, the set of all BITS professors, if you are talking this particular predicate with respect to BITS University. Universe of discourse for y is set of all students registered to BITS University. Actually, if you have to understand the power of predicate logic, basically when we are saying it is distinguishing subject from the predicate, the main advantage that we are getting here is we are able to state things about many objects at once, which we can't do so nicely in propositional logic. We can state a fact about many objects at one go. We will take an example. Let us consider a proposition called px is x plus 1 greater than x. This is the proposition that we are considering. Say universe of discourse, I say it is going to be set of natural numbers, and the predicate that I am talking is px is equal to x plus 1 greater than x. This is the predicate that I am talking. Then in one single sentence I can say that for any number x, px is true. I can say it in one sentence. If similar thing, if I have to do in, say, probably propositional logic, you can do it better, but rudimentarily if you have to do it, you have to do it like 0 plus 1 is greater than 0, 1 plus 1 is greater than 0, 1 plus 1 is greater than 1, 2 plus 1 is greater than 1, and you have to put and between all these prepositions to say a simple statement that any number, if you add 1 to any number, it is going to be greater than 1. If you have to represent in propositional logic, you may have to do it you have to do this way, whereas this predicate logic gives us power to do it so nicely in one sentence, that is, for any number x, px is true. You will be able to do it. You will be able to state a fact about many objects at one go. That is the power that it gives. I really I would here to get the difference basically. Of course, in proportional logic you may be able to do it better in this particular example, but there are lots of examples where proportional logic basically fails to express, to state a fact about many objects at one go. Okay. Basically, when I say using predicate logic, I can state a fact about many objects at one go. I am making this statement because of some quantifiers that are there in predicate logic. Basically, quantifiers provide a notation that allows us to quantify, count how many objects in the universe of discourse satisfy a given predicate. The example that we go back and see, if I say X is sleeping is a predicate that I am talking, and universe of discourse happens to be set of all human beings, then I should be able to say all the human beings are sleeping, or some human beings are sleeping, or one human being is sleeping at a given point of time. I would like to quantify how many objects in the universe of discourse satisfy a given predicate. To say this, we have a couple of quantifiers. One is for all and another is there exists. For all, this is how we symbolize it. Basically, it is just writing A in a reverse way. For all, you write generally like this, isn't it? So if you just reverse this A, you get this symbol. Maybe that is what the just people might have come up with this particular symbol. For all, or people call it universal quantifier. What it means is, when I say for all x px, means for all x in the universe of discourse, my predicate is holding good. If I say, just for argument's sake, if I go back to my original predicate, px is equal to x is sleeping, and I say for all x px, what does it mean? It means all human beings are sleeping, which is true or not. Let us not debate on this. This is a proposition. It can take either true or false value. I will be able to basically quantify how many objects are satisfying my given predicate. I can say all human beings are sleeping. Its truth value happens to be false. That is a different thing. I will be able to quantify all the objects in the universe at one go, isn't it? In this case, for this example, this happens to be a false. That is a different thing altogether. I am able to quantify all the objects about my predicate in one go. That is the power of that is the significance of quantifier. Let us see another quantifier, that is there exists. When we say there exists again, this particular symbol probably might have come like this. Actually, you write exists like this, isn't it? Exists. This is what we write in English. People might have just reversed it. I don't know. Maybe that might be true. There exists is also called existential quantifier. When we say there exists px, it means that there exists one object in the universe of discourse which is satisfying my predicate. In our example, when we say our predicate happens to be px is equal to x is sleeping, I say there exists x px. It means that there is a human being who is sleeping, which is very much correct at any given point of time. Most of the times, at least one human being must be sleeping. In this case, this preposition assumes the true as its truth value. Basically, it means to say that there exists x px means there exists an object which satisfies my predicate. There exists a human being who is sleeping now. Okay, this is how they are defined. And let us understand these these quantifiers with better examples. Suppose my universe of discourse for the variable x be parking spaces at bits, and my predicate happens to be, I am defining my predicate as x is full. This is the predicate that I am speaking, and x universe of discourse is parking spaces at bits. Then when I apply this universal quantification of a px, that is for all x px, what does it mean? It means that all parking spaces at bits are full. When I say for all x px, it means that in English it means as that all parking spaces at bits are full, or equivalent meaning to it, equivalent English meaning to it, every parking space at bits is full. For each parking space at bits, the space is full. All these are English equivalent statements. Basically, it means that it only says that there is all parking spaces are full. This is what the English meaning of for all x px. Let us take another example for existential quantifier. The same thing, universe of discourse happen to be parking spaces at bits, and px is the predicate x is full. Then the existential quantification of px, that is there exists px. What does it mean by there exists px in this example? It means that some parking space at bits is full, or equivalently it means that there is a parking space at bits that is full, and equivalently at least one parking space at bits is full. This is what it means by there exists px. There exists an object in the universe of discourse for which your predicate is true. We will see one simple example. When I have got two predicates, px, that is x is say some university professor, UW professor, and gx is x is genius. What does it mean by there exists x, px and gx? Just think about this. What does it mean? It simply means there exists a guy. If basically this universe of discourse happens to be the set of all human beings, it says that there exists a human being who is UW professor and he is genius. Or otherwise equivalently you can say there is at least one UW professor is genius. This is what precisely it means by there exists. So let us speak about some terminology. This is nothing more than terminology. When we have got variables in a preposition, we call them free or bound based on how these quantifiers are working on them. If no quantifier, say I have got a simple predicate like this, say this is a predicate called x is married to y is being represented by pxy. This is a simple predicate that I am speaking, and I don't put any quantifier before pxy. I say both these variables are free. Suppose I say for all x pxy, suppose I say this, then it means for the variable x I am talking a quantifier, hence x becomes bound variable, and because there is no quantifier that is working on y, y remains a free variable. Let us see these things with better examples. So I just say pxy without any quantifier, it very much means that it has got two free variables because there is no quantifier working on them. And I say for all x pxy, how many free variables it has got and how many bound variables it has got? Obviously it has got one free variable and one bound variable. Which is which? Because for x there is a quantifier that is working on it, it becomes a bound variable, and there is no quantifier that is working on y, hence y remains a free variable. Let us take another example. When I say a statement like px where x is equal to 3, this is bound because I am giving a value to x, and if you have got no free variables in a predicate statement, for example I say there exists x px where px happens to be x is sleeping, then there are no free variables. Okay, it means that there is one human being who is sleeping. This becomes a preposition. You have got basically a predicate and you apply quantifiers to it, and it doesn't have any free variable, then that particular statement will become a preposition, and hence it will have a true or false as its truth value. In this example, px is x is sleeping is the preposition that we are talking. When I say there exists x px, it means that there is a human being who is sleeping, which is very much a preposition. Unless otherwise there are no free variables, it remains a predicate. For a predicate to be a preposition, it should not have any free variables. For example, we have got a predicate called pxy, something like pxy is defined as x man, and say x is friend of y. Then for all x pxy, what is happening over here? You are bounding the variable x, but y remains the free variable. This is still a predicate because there is a free variable, and that predicate can be well called as qy, which is again a predicate. Let us take this simple example. Let us define a predicate called lxy. What I mean by how I am defining lxy is x likes y, and of course my universe of discourse for x and y are people, set of all human beings. Then what does it mean? There exists y lxy. In English we have to understand this particular statement as there is someone whom x likes. It means lot of things, isn't it? There is someone whom x likes. You take any x, there is going to be a human being who is liked by x. So this is again a predicate with one free variable x. Let us take this particular statement. For all x there exists y lxy. What does it mean? For every person there exists another person whom he likes. Everyone has someone whom they like, equivalently say. Because this particular guy, this particular predicate doesn't have any free variables in this case, this will be a very much a preposition, and definitely preposition will have 0 free variables. Okay. About free variables, let us see one more thing. We will take this particular statement, for all x there exists x p x. Is it a valid statement? It is not a valid statement, because when you have this particular statement, this becomes very much a preposition. For a preposition, you cannot talk of any variables being in it. So this is not a valid statement, because when you say for all x and something, x should be variable in the next portion of what you are talking, but this happens to be a very much a preposition which is not having any of the variables. Whereas if you consider this particular statement, for all x p x and q x, this becomes a preposition because it does not have any free variable, and this still remains a predicate which is having only one variable. It is not a complete preposition, but it is still a predicate. If you see this particular thing, for all x p x, what does it mean? This means there is one variable and it has been bound, and hence this is a preposition, and there is one variable and it has been bound, this is another preposition, and there is and between these two prepositions, and this remains a compound preposition, and hence it is very much legally a preposition. Let us take this particular example and see what we mean by English when we write a statement in predicate logic. Let us take this particular example. I am defining Rxy as x relies upon y. This is the predicate that I am talking, and universe of discourse of course is the set of human beings for both x and y. Then what does it mean by for all x there exists y Rxy? Just think about this. Rxy is x relies upon y. Then what does it mean by for all x there exists y Rxy? It means that for all human beings there is another human being whom they rely upon. Precisely speaking, in English it is something like this: everyone has someone to rely on. This is what the English equivalent statement of the predicate statement that we just spelled some time back. And what does this statement mean? There exists y for all x Rxy. What does this statement mean? It means there exists a person on whom the whole world relies upon. There exists y, there exists one person for all on whom all human beings rely on, and for fun's sake you can say that there is a poor overburdened soul whom everyone relies upon, including himself, of course. And what does this statement mean? There exists x for all y Rxy. It means there is a person, he will rely upon the whole world. Basically, there is some needy person who relies upon everybody, including himself. That means he needs everybody for him to survive. Of course, in English you can write a number of ways, but finally the meaning is the same. Semantic of the English is going to be the same however you write it. What does this mean? For all y there exists Rxy. It simply means everyone has someone who relies upon them. You take any person, he will be relied upon by some other person. For all y there exists x or xy. And the last statement means for all x, for all y or xy. It means that everybody relies on everybody else in the world. Not else actually, including themselves. Everyone relies upon everybody. So this is how we have to translate the given predicate or preposition, predicate statement, predicate preposition into English. It's little bit difficult at the first go, but one has to practice it. And there is one more convention. This is just a convention, nothing more than convention. And whenever you need to write something like for all x greater than 0 px, okay, whenever you have to write like this, actually traditionally you need to write like this, but people do write like this, for all x greater than 0 px. Is perfectly fine. This is just a notation, nothing, is a convention. Instead of writing for all x, x greater than 0 implies px. People can write for all x greater than 0 px. It's just a convention, nothing more than a convention or notation. Like we have seen in propositional logic, here also there are some equivalence laws. Let us see them. I mean, very definition of quantifier, though I have not spelt it till now, it actually means this, isn't it? For all x px, when I say this particular thing and say my universe of discourse happens to be ABC, that means my universe of discourse may be countably finite or countably whatever it is, it's a set which is having lot of objects. When I say for all x px, it is equivalent to saying PA is PA, PB, PC, PD, and it is all. You put and the preposition is going to be you just substitute your x with it. Basically, for all x px means for all the objects that x can assume, P of that object is true. It is equivalently saying that PA and PB and PC and so on, where A, B, C are objects of the universe. Similarly, when you say there exists x px, what does it mean? It means that there exists an object in the universe of discourse for which for which the predicate is going to be the PA is going to be true. We don't know what that particular object is. Hence, you can nicely write it may be true for A, it may be true for B, it may be true for C. We don't know, but because we are putting R, you get the same meaning. We don't know for which element this P of x is going to be true, but certainly for one element it is going to be true. Hence, I can write the whole thing as PA or PB or PC or PD and so forth. And from these we can prove in fact these two small laws, that is for all x px is equivalent to not of there exists not of px. Let us see how we can prove this. This is very simple. If you understand, if you remember De Morgan's law that we have been speaking in the last class, let us see how we will do it. What I would like to prove over here is, we need to prove that for all x px is equivalent to not of there exists not of px. We have to prove the equivalence of these two statements. What I do probably is I will take this particular statement and I will derive the another statement. Let us see how do we do it. Let us take this particular thing, there exists not of there exists x not px. Basically, let us here apply what does it mean by there exists x and say just think this as qx, there exists x qx. Just go back to this particular thing, what does it mean by there exists x px? it is PA or PB or PC. So when you just apply this, what you get over here is not of PA or not of PB or not of PC, because this whole thing is QX. Just imagine that. Then there exists XQX. It means that Q of A or Q of B or Q of C or Q of D, hence and so forth. Q is nothing but not of PA, so I can write for this guy I can write not of PA or not of PB or not of PC, hence and so forth. And if you remember the simple De Morgan law, not of P or Q, when we have got this not of P or Q is equivalent to not of P and not of Q. This is the De Morgan law that we have seen in the last class. Not of P or Q is same as not of P and not of Q. Just apply the same De Morgan law over here. When you have got not of, say there are a number of prepositions here, you just have to negate each promotion, each preposition and put the and operator in between them. You negate this guy, what do you get? Not of not PA is PA. You negate not of not PB is PB. Not of not PC, not of not PC is PC, and you have to just get the and operator by very means of De Morgan's law, and hence you get for all x Px. This is how we prove equivalence, and similarly one can prove the other equivalence also. Having proved De Morgan laws, we just proved it. And similarly with the similar way of doing it, one can prove that not of for all x Px is equivalent to there exists not of Px. This also one can prove. Just apply what it means by for all x Px, not of PA and PB and PC. Then you just take this negation inside using the De Morgan's law, you will get it. Just practice it. It's definitely on the similar lines that we did just discuss now. Let us see some more equivalence laws. So it really doesn't matter in this case for all y Pxy is equivalent to for all y for all x Pxy. It really means that you don't worry where you put whether you put for all x in front of before for all y or for all y before for all x. It really doesn't matter. The similar case with there exists also. And here this is little interesting. For all x Px and Qx is equivalent to for all x Px and for all x Qx. Similarly, there exists x Px or Qx is equivalent to there exists x or there exists Qx. In fact, you can prove in the similar way that I proved the last thing. It's simple. One should practice it and do it. Here only practice works here. You need to practice a number of problems to get a firm grip on this. Okay, what I mean here is this x, when I say this x for all x, this is working on this and on this as well, so that I will get this and this, and yeah. To conclude today's session, what we have understood today is what a predicate is and what are the objects inside a predicate are, and what is the benefit that you get out of predicate logic, and when do you say a variable a free variable or a bound variable, and we have seen quantifiers like for all and there exists. Okay, and we have seen where all it is applicable. Thank you. We will see you in the next class. Bye.